Today's final talk, Koji Fujiwara, stable commutator length on mapping class groups.
Thank you, Mark. And I'd like to thank the organizers, Real Miha, for the invitation. And it's a great honor to speak here for the conference in honor of RIPS. Happy birthday. Okay. So this is the joint work with Bestabina and Bromberg. It's going to be about the stable commutator lengths on the mapping class groups. So let me define the stable commutator lengths. So you have a group G, and then you have a commutator subgroup like this, and this group consists of an element which is a product of commutators, like this. Okay. And each one is from the group G. So the commutator length of the element G I write CL of Z is a number of commutators you need to write G as a product of commutators. But so you have n commutators here. So there is it's not a unique way to write it. So just take a minimum of such n. So that's the definition of commutator length of G. Topologically, if imagine that your G is a pi 1 of some space X, then I just draw a picture like this. You have a surface of genus n, which is exactly the commutator length of G, and this boundary curve is for G, and then you have AI and BIs in the standard position, like this is A1. I don't know, maybe this doesn't matter. This is A1 and this is B1, and I need a second one. This is A2, and then you have B2 like this. So, so on this surface, the relation you see from this surface is exactly this equation. And if there is no G, it's exactly the relation to define the pi 1 of the surface. And so maybe I write this surface sigma for G. Okay. All right, so now I'm interested in how this commutator length grows if I take a power like this. And you notice that this sequence of numbers is subadditive in the following sense. So n plus m. The commutator length of G to the n plus m is not more than commutator length of G to the n plus commutator length of G to the m. So this is obvious because if you can write G to the n by, say, k commutators and G to the m by L commutators, then of course you can write G to the n plus m by k plus L commutators. Maybe it's a bit less. That's why it's not equal, but just inequality. So this sequence is subadditive. Okay. And if you see a subadditive sequence, what you do is just divide it by n and go to limit. So that's what I do. So and just divide it by n and go to limit. But it's a theorem that the limit coincides with the inf. So in this case, it's a limit. It's a little theorem. And goes to infinity, and that's a stable commutator length of G. So this is a stable commutator length. Okay, so SCL is a function on G prime to non-negative numbers, and so the one advantage for you to go to limit like this is that this function becomes linear in the following sense. So SCL of Z to the n is n times SCL of G. just because it goes to the limit in this way, therefore SCL of G to the n is n times SCL of G. And also, what you know about this function? Well, this function, it's constant on each conjugacy class. That's true even before you go to SCL. It's true for CL, but I'll just write this as SCL of the conjugate of G is SCL of G. Okay. You can see it because if you just take a conjugate of G, you can just take conjugate of all of them, and that's why CLG is same as CL of the conjugate of G by A. Okay, what else do we know? Well, so SCL of trivial element is 0 because this is because of the definition. So trivial element, for example, is the commutator of A, and just divide it, power of 1 is 1. So that's what you know. Okay, so I introduce one convention. If the element is not in G prime, then let's say commutator length of G is infinite, because you can't write it as a product. So there's just a commutator length is infinite. And then using wait, this is definitely, yeah. So and then and using this definition, you define stable commutator lengths. That's why. So I wrote inf, not limit. So let's use this inf definition. Then this becomes a function, on entire G to the non-negative number and maybe infinite. But as Ilya pointed out, if G prime has a finite index, every once in a while, if you take a power, then it becomes a member of G prime, then the CL is well defined. Therefore, in this case, you have a function. It's really a function in this. Okay? So every once in a while, this is in G prime, therefore commutator length is just a number. Therefore, you go to you use this definition, SCL is also a number. Okay, so this is the definition, and we like to say something about this function on G. Okay, so here are two extreme examples where a commutator, you know something about the stable commutator lengths. So example 1. So if G is a free group, 1, and then so color has shown any element G, non-trivial, stable commutator length of G is at least 1/6. Okay. So you have this function, so you can talk about the image of this function, which you may call spectrum. So as I said, 0 is in the image. This is in the image, but the theorem says for the free group, so there is a gap in here. And you don't know what's going on here, but so there is a certain gap in here. That's what color showed. The other...
Could you give an example of an element with
the lowest?
Like between 0 and 1?
I don't know. I don't remember.
Okay.
Yeah.
It's for any G in the group, not in the commutator?
Yeah, maybe it's infinite. So I'm using this convention here.
It's at least. Okay.
Yeah, maybe it's infinite. Yeah. Right. So the other example is a lattice. So, for example, SL and Z in SL and R, and at least 3. And then it is known that actually stable commutator length vanishes. So if you, first of all, it's known if the commutator sub is everything, then you call it perfect. And also, you know, stable commutator length vanishes. It's more than that. So you know there exists a constant C such that for any G in SL and in Z, commutator length of G is at most C. Okay. So in particular, if you go to the limit dividing by n, of course, it's going to be 0. So this is a stronger statement than this. So for this property, you call it uniformly perfect. So this is only for S and Z, but also for any other lattice in here, higher rank, it is also known that stable commutator length vanishes. Actually, first of all, for this one, it's a theorem by, I think, Matsushima, that this has finite index. I think it's a theorem by Matsushima. And this one is theorem by Berger-Monod. And as far as I know, it's open if it's uniformly perfect. But they know that they managed to show that stable commutator length is constant to 0.
Gamma is lattice, right?
What? Lattice. Sorry, lattice.
What is open? Can you repeat?
Yeah, if it's uniformly perfect, or even in each cyclic subgroup, if this CL is bounded or not.
So when you say Berger-Monod, do they rely on Bavard?
Yes, yes. Okay, so those two are the extreme examples, I would say. So one is always positive, or uniformly positive, and the other one is constantly 0. Then I like to mention a theorem by Denny Calgary, who showed if you take a closed hyperbolic manifold, and if G is pi 1 of the manifold, then actually this group is like a free group as far as the stable commutator length is concerned. Namely, exists a constant C, so that any non-trivial element in pi 1 SCL of G is at least C. What? So in this sense.
No dimension restriction?
No. Dimension 1 I don't like. Dimension at least 2. Yeah.
No, 1 is okay.
What?
1 is okay.
No, 1 is Z, then it vanishes.
No, it's okay.
No contradiction.
Oh, you're right. You're right. Dimension 1 is fine too.
But for high dimension, don't you have, aren't pi 1 the 5-dimension hyperbolic lattices?
Yeah. So what?
Didn't we say that lattices have...
This is higher rank.
Yes.
This is like 1.
This is rank 1.
Okay.
So so there is a sort of dichotomy.
If you fix the dimension, is it known whether there's a C that works for all manifolds in that dimension?
I don't know, but I guess no. But I don't know.
Conjecture, no.
Yeah, but I don't know. So the theorem I'm going to state later is like this one. So let me prove this theorem. At least let me give the idea how to prove it. And this idea I read in one of the paper by Gromov. He wrote like few lines why this kind of statement is going to be true. And this is the argument we are not we're not going to use this kind of argument for our theorem. And also, Denny, his argument is different too, but since I like this Gromov's idea, so let me explain. Then it's clear what's behind the positivity of stable commutator lengths. So you have an element in the commutator subgroup, and this one you really have a manifold. And first, it's non-trivial, so I realize it by a closed geodesic. So this is a closed geodesic for G. And since it's a commutator subgroup, as I said, it bounds a surface, immersed maybe. It's not embedded maybe, but it bounds the surface so that this genus is commutator length of G. Okay, and I write it sigma G. Now Gromov says just take a minimal surface. So there is a surface bounding this curve in this homotopy class. Take a surface as a least area. All right. Now you have a minimal surface in the manifold. Then here is a fundamental result for minimal surface. So any point P on the surface, you can talk about the curvature at that point P on the surface, because it's a Riemannian manifold. You have a immersed submanifold. You can talk about the Riemannian metric there. So you can talk about a curvature there on the surface. And also, of course, you have a curvature in the manifold. You always have this inequality. The curvature on the minimal surface is never bigger than the curvature in the ambient manifold. So the reason is because if it's more curved, so imagine you are in the Euclidean space, and if you have a minimal surface, and if it's more curved, it means positively curved, then it's like this, and you can push and make it the area smaller, contradiction. So that's why this inequality is true. But you know this is -1. Okay, because this is a hyperbolic manifold. Okay, now I use Gauss-Bonnet. To sigma. Okay, so let me write. Maybe I write it here. So Gauss-Bonnet says if you integrate the sectional curvature on sigma, then it's going to be 2 pi over Euler characters of this one. This is Gauss-Bonnet. But I can compute this. So what is this? Because this genus CAG, one puncture, therefore this is 2 pi times 2 minus 2 times commutator length of G minus 1, because there is one puncture. That means this is 2 pi minus 4 pi commutator length of G. Okay. On the other hand, as I told you, this function is at most -1, so I integral, then this is at most minus of area of the surface. Okay, so I just move it around and I get, therefore, this area of the surface is at most 4 pi times commutator length of G minus 2 pi. So this is what I get. Okay? So this is for geodesic for G. But actually this is true for any element. So now I do it for, so this is for G. So do it for G to the n. Then I get area, the minimal surface for G to the n is at most 4 pi times commutator length of G to the n minus 2 pi for any n. All right? So now this is maybe G to the n. Okay. Now I like to estimate the area of this surface from below. So you have a geodesic boundary, So I look at the color like this of the side with the C. Okay, so it's like annulus, so it's nearly product. So that means you have a lower estimate like length of this closed geodesic for G to the N times C. Okay, but this is a closed geodesics, and G to the N is just go around N times on this closed geodesic for G. So this is N times length of G times C. Okay, so now I divided this inequality by N. So length of G times C is the most N 4 pi commutator length of G to the N minus 2 pi divided by N. So I go to the limit. So it converges to 4 pi stable commutator length of G. By definition, because CL of G to the N divided by N go to limit. Okay, but this one is the length of a closed geodesic. For G, there is a lower bound by some injectivity radius because it's a closed manifold. So like injectivity radius, so this is at least 2 times injectivity radius of M times C. Okay, therefore, so I get that 2 injectivity radius of M times C divided by 4 pi gives a lower bound of stable commutator length of G.
Could you repeat what is C?
Yeah, I don't, but I say. Yeah, good question. So Gromov didn't say that part, but okay. So you're right. So this is a color, okay. So that this, annulus color is embedded in this surface. Okay. So secretly, I'm sort of hoping or using that. So strictly speaking, this constant should depend on G and N. May depend on G and N. So the secret is that if there is a uniform positive lower bound for this constant C, this is a perfect proof. But you have to prove that. Otherwise, maybe this constant C goes to 0, so then the proof breaks down. So yeah, so that's a little issue here. Okay, good. Another question people may ask is, does minimal surface exist? Who proved it? So I don't know. Maybe Yao. I don't know. So anyway, but still it says it indicates that negative curvature tend to say give positive stable commutator length. It's sort of clear from this kind of arguments. That's why I did it. So the point is, if you want to prove stable commutator length is positive, you have to find the negative curvature.
So would it carry on if I assume just there is a bound on the curvature?
Upper bound.
Yes, upper bound.
Yeah, that's fine. So maybe I write you a theorem, one theorem. I proved this theorem a while ago. So if G is a world hyperbolic group, and then for any element G, stable commutator length of G is trivial if and only if there exists a constant n, an element H, so that G to the n, H minus is G to the minus n. If G to the n is conjugate to its inverse, then that's if and only if condition the stable commutator length is going to be 0. And moreover, exists a constant C such that if stable commutator length of G is positive, then actually it's at least C. Okay. So for the manifold case, closed manifold case, this one, so this is this part. So you only have to say that this is not going to happen in the manifold case. It doesn't happen because in hyperbolic group, if this condition happens, H has to be a torsion. But there is no torsion in the manifold case. Therefore, it never happens unless G is trivial. Therefore, if you don't care about the constant C, this theorem is more general than this one. Okay, and this condition, not in that paper, but in the paper with Besivina and Bromberg, we say if this happens, then we say G is archival. Because so the inverse is like a mirror image, and the mirror image same as U, then you call it archival. And otherwise we call it chiral. So we just introduced this terminology. Okay, so in other words, I'm saying in the hyperbolic manifold, any element, non-trivial element, is chiral. Okay, so another ingredient other than we found this condition is that we didn't use minimal surface. To prove this, we used the quasi homomorphism instead of minimal surface. I mean, nobody uses minimal surface, but so we didn't use that either. So, but I'm not going into detail of this one. And also, of course, in the free group, in Carr's statement, so any element, non-trivial element in free group is chiral too. Okay.
Is it easy to see why this a chiral condition applies to the second commutator length is 0?
Yes, yes. Let me. Yeah, sure. Thank you. So this direction. So this is easy. Let me do it. So H G to the n, H minus E, G minus n. Okay. Therefore, H G n, H inverse, G minus n is G minus 2n. Clearly. So therefore, but this is a commutator, one commutator, as you see. So it means the Sierra G, you take the inverse. So this is 1 at most 1. 1 at most 1. Okay. Now you take a power of this one. So you know, like G NL H inverse is G minus NL. So it implies a commutator length of G to.
Yes. 2NL.
Where do I make a mistake?
2NL.
2NL, yes, okay. 2NL is 1 for any L. Therefore, SCL of G is trivial. So there is no geometry, just a little algebraic exercise. Okay. So this is 1. And 2, we also proved that if you have an element in mapping class group of a surface, and I assume this is Sudan-Ossoff, then the same conclusion is true. So stable commutator length is 0 if and only if G is achiral. Namely, you know, in mapping class group, you find the H and G to the n is conjugate to G to the minus n. And also, this is true. Exists a constant C such that if this is positive, then actually this is at least C. Okay. So idea, the basic idea behind proving this theorem is, first of all, I told you we are not using a minimal surface, but instead we are using quasi-homomorphism. But still, the idea here is important. So we still need or use So group G is acting on some hyperbolic space, and the concerned element G is hyperbolic on X. Hyperbolic means here, so I told you in the beginning, so it is represented by closed geodesics. So in the universal cover, there is an axis and it's a hyperbolic isometry. That's important. So those three ingredients, at least I need it for my argument. So space is hyperbolic, and your element is hyperbolic. Okay? So this one, it's obvious what you take for X. You just take a Cayley graph, action on G, any element is hyperbolic, so fine. And this one, we use a curve graph. So this one, so this is it acts on the so-called curve graph. By Mazer-Minsky, it's proved that this is delta hyperbolic. And also importantly, element in here is G is hyperbolic on this curve complex, if and only if G is pseudo-Anosov. So then, you are in this picture, so you try to use this quasi-morphism argument and show. So this direction is easy, so you work hard on this direction. Okay. All right. But so this is one result for stable commutator length for mapping class, which is only for pseudo-Anosov. But it's clear why our argument works only for pseudo-Anosov, because except for pseudo-Anosov, we don't have this hyperbolicity of the element. But nevertheless, there is the other theorem, the other case, which is known. So that's a theorem by Endo and Kochik, who says if you have a mapping class which is then twist, then they prove the stable commutator length is positive. Okay, so they proved it. So so I couldn't reprove it because I didn't know any space for mapping class group act on, which is delta hyperbolic, and then twist is hyperbolic. So I couldn't reprove it for a while. And of course, I like to make a comment. Of course, any then twist he has positive stable commutator length. That means any then twist is chiral, because otherwise it's going to be 0, because this is always true.
So for this conclusion, do you need more than just hyperbolicity of the action? Do you need something like WPD or whatever?
For which, this one?
Yeah.
For this one? Good.
You must need something else, right?
Yeah, of course, plus something. Yeah, plus something for the action. Otherwise, I just state, the theorem, group G acting on delta hyperbolic, so the element is hyperbolic, then positive. No, you need something on the action. But yeah, right. So I didn't say the whole action is proper. Yeah. So it can be less than that, because this action is not proper. This is just WPD or a cylindrical or whatever. Okay. Yeah. So we need some.
But do you get such a theorem for outer fan or for the reducible elements?
I think so. Yes. Yes. I mean, okay, fully reducible. I think exactly it has positive stable commutator length, if and only if that is chiral. I think so. No. Okay. So to deal with the general mapping class, let me review briefly the Nielsen-Thurston classification. Classification for the element for mapping class. So you have a element in the mapping class group. So we already heard, so this one possibility is pseudo-Anosov. second, then twist. And maybe third, it's torsion. Okay? I wish this is the whole classification. For torus, actually, it's fine. So mapping class group of a torus is SL to Z, and for any element in here, for the torus, it's either anosoph or power of then twist or torsion. So that's exactly when. So this is 2 by 2 matrices. So you can, if you can diagonalize in SL2R, then that's anosoph, and then twist it's like a power of then twist is like this, and the torsion is torsion. So that's a whole classification. If the genus is bigger than 1, and then it's a little bit more complicated. So so if you have any element G in mapping class group with a surface, then so it's going to be like a Jordan normal form for the matrices. So you have a surface here, and for any given element G exists a system of disjoint simple closed curves, say like this, and this system is invariant by the fixed element, the given element G, and if I cut this surface into pieces using this sigma I, so in this case you have S1 and S2 and S3, so S I just divided into subsurfaces by this curve system, and exists an n, so that if you take a power G to the n, so maybe each G, this G permutes the pieces. In this case, maybe it permutes S1 and S3, but if you take a power, so each piece is going to be preserved. So Gn, each one is invariant, and if I write G to the n, if I restrict G to the n on each subsurface and I get Gi, then G to the n is written as a product of those. Say M, and then Gi and Gj commute, because different one has a different disjoint support, so therefore they commute. And each Gi is either 1 or 2. I mean, Susanov or power of then twist. So that's the general picture. So each piece, it's one of them, but you have to divide it into pieces. And you want to, I take a product and power because maybe it's a torsion. So the maybe if it's torsion, G to the n is just identity. Okay. So this is a description of each element. Okay. That said, I like to mention another condition than this curarity, which forces SCL to vanish. I don't know. Do I want to keep this? Maybe not. Where? Oh, yeah, you're right.
Yeah, but it's much more successful if you don't move around the board.
Thank you. Then I follow your advice. Okay, another condition. What the other condition? I need a longer chalk, maybe. Where is it? Chalk? Maybe it's in here. Okay, fine. Yeah, thank you. So it's a bit more complicated than the other one chirality. But so suppose you have element G, and suppose you have two elements A and B in G, and G is written as A, B, A inverse, B inverse, and A and B, A inverse, B inverse commute. So that's assumption. Then SCL of G is 0. Okay? Let me prove it. It's trivial, but so G to the n, so they commute. By the way, it's a commutator, but additionally they commute. I assumed it. So G to the n is A to the n times B, A to the minus n, like this. So this is one commutator. So that commutator length of G to the n is 1 for any n. Therefore, stable commutator length vanishes. Okay? So this looks like a naive condition which guarantees SCL vanishes. And more generally, it's same as this one as idea, but it looks more complicated. So G is a product of A and 1, B2, A and 2, B2 inverse, B L A and L B L inverse, so that they commute. I have any element, but they commute, and also the sum of the exponent is 0. Then SCL of G is 0. Okay? Exactly same proof. G to the n. So everything's going to be to the n. But you have n1 here. So maybe before take a power. So, but the sum is 0. So you move minus n2 here, minus n3 here, a to the minus l here, and then each one becomes a commutator. So it's exactly same reason why this implies SCL of G is 0. So this is an important assumption. So here 1 plus minus 1 is 0. That's exactly what I'm using here. Okay. So I say this is the other condition, maybe say 2. And the previous chirality is the first condition. And now I combine those two, and that's as well a condition which forces SCL to vanish. So let me write, but actually that's in view of this Nielsen-Thurston classification of the element. So combining in chirality dt, and this condition, so you have an element G and exist n, so that G to the n is a product, and any Gi, Gj, Gj commute. And now I reorder G1 to Gn in the following way. First, I look for, combining A chiral. So A chiral forces SCL to vanish. Chiral is the other way around. So first I look for chiral elements. So maybe I just write it A. I don't know how many you have. So this is chiral elements among those. And then the rest, chiral elements, I'm doing grouping up to into conjugacy classes. So reorder and grouping. So the first one maybe B1, I1, dot dot b n I to the n, so that b I bj commute, and the exponent, the sum of the exponent is 0, and you have the other conjugacy classes, so I just write it in this way. I don't know. And they are conjugate. So in this group, so they are, those bi, bj are conjugate to each other, then the sum of the exponent is 0. Then stable commutator lengths of G vanish. You just do the same thing. You take the power, and this achiral element just sort of die in itself. And then the other ones, so they kill each other by this kind of argument. Okay, so here is the theorem. I don't know, just a weird BBF. So you have an element in mapping class group. Then stable commutator lengths. Actually, let me write, so I just write this condition star. Okay. Is 0 if and only if. So for Nielsen-Sarston class, description of the element G, so you do it, and if you have this condition, then that's exactly when stable commutator length vanishes. For Nielsen-Sarston, I will say normal form for G. Okay, so that's the main theorem. And moreover, so it exists L, so that if stable commutator length is positive, then it's at least L. And also exists K, such that if stable commutator length vanishes, then actually commutator length is bounded. It doesn't grow.
So for example, what your theorem says if your mapping class is just pseudonymous of on one piece.
Yes? One piece.
So there is a piece where you have something pseudonymous of and
Yeah.
everywhere else.
Yeah. So same as Danny. So then SCL is 0 if and only if it's chiral. Also, it recovers Endo-Kochik theorem because the end twist is just the end twist in this description. It's never like this kind of product. It's never chiral, therefore it's always positive. So we found another argument because the argument was using this Seiberg-Witten theory for full manifolds.
So you have effective way to check whether you can write this element, given element.
Yeah. So algorithm. So if you have algorithm to write down this Nielsen-Sarston normal form, that's one thing. And if you can check this, this kind of conjugating thing, then you can check it, because you like to see if it's chiral or not. So for that, you have to know, if some of them are conjugated to each other or not. Okay. So for this one, of course, this direction is easy. Easy means it's always true for any group G. So this is a work. You have to do something. So first of all, we need an action or the action on delta hyperbolic space X so that the concerned element G is hyperbolic. For example, for Dane twist, you have to find one. So for that one, I state one theorem which is not in another paper before the paper for stable commutator lengths, but we found a way to produce so hyperbolic space for a group to act on under certain circumstances, and then if you apply that machinery, we found some action like this. So mapping class group on the surface act on a space X, which is a product by isometries and properly, and preserving this decomposition, product decomposition, such that each gamma I is delta hyperbolic. Second, any element in mapping class group in infinite order is hyperbolic on X. And this is more or less enough for to prove the theorem, but I just state one more property which was important for that paper, so that although this action is not co-compact, so it's not true that mapping class group is Qi to this product space X, but however it is Qi quasi-isometric to its image. So I just write it. So if you embed mapping class group into the space by orbit, maybe mapping element, I fix a base point in here, just move around by the action, then this is Qi embedding. Okay?
X is product of what?
Delta hyperbolic space.
And this is metric product?
Yeah.
So X is not delta hyperbolic.
No.
Okay.
Yeah. No. Otherwise, you can embed no. Yeah. No. Yeah. So how do we finish or proceed for the proof of this theorem? So I told you this action preserves the decomposition, but it doesn't preserve each of the factor. It may permute, but there are only finitely many of them. So if you go to the finite index subgroup, it preserves each of the factor. So because there exists some subgroup, finite index, so that each one is preserved. And so now you have a given element G. So if you take some power, it's going to be in H because it's a finite index. And it is hyperbolic, as I said, if it's an infinite order on X, but it preserved each factor, so it must be hyperbolic on one of them. Is hyperbolic on some gamma I. And now I come to the point that how good is action, because this action was proper, but now I just look at the one factor, so the action on that factor is no more proper. It's highly improper. Nevertheless, I just write it. We prove this action on H on gamma I with respect to this element is weakly properly discontinuous. This is something we defined and proved, and with this assumption, you can produce quasi homomorphism on H. This is sort of a standard Brooks types argument, and then it shows under this assumption, I mean I mean, if G doesn't satisfy this star condition, then you prove that stable commutator terms G to the n is positive in H, but then you argue a little bit more, and it's positive in mapping class group of the surface. One last comment is that, for example, this property that element G, for example, even for Dehn twist, is acting hyperbolic isometry on this one, is good, because once you have an action of the group G, so that some element is hyperbolic on there, you can show that that element is not distorted in the group G. So this implies G is not distorted in the whole mapping class group. So it shows any mapping class of infinite order is not distorted in the mapping class group. That's a theorem by Farber, Labotsky, and Minsky. But we found another sort of obvious consequence from this theorem. So I stop here. Thank you.